Alright, silly people, here's the situation. We're meant to find the matrix representations of Jx and Jy in a spin 1 system, whose eigenvectors I've written on the right there. To do this, we don't know the eigenvectors of Jx and Jy off the top of our heads, but you can solve for them using the definition of J plus and J minus, which is Jx plus or minus ijy. Let's then just solve for Jx and Jy in terms of J plus and J minus. So J plus will be Jx plus ijy. Solve for Jx minus ijy is equal to Jx, and then plug that into the J minus equation, which will read J plus minus iji minus iji then, which means, let's just move this to the other side. J minus J plus is equal to minus 2ijy, and then divide by minus 2I to get J plus minus J minus, where 2I is Jy, and then plug that in back to the equation for Jx, which will go like Jx equals J plus minus J plus minus Ji, or J plus minus J minus over 2. So you'll end up with J plus J minus over 2. Okay, we have those. We have the definition of the matrix forms of plus or minus J minus. Whatever. I'm just gonna drop that in. It's this definition here. Okay. Let's just plug that in for Jx then. Jx will be, I'm going to factor out a h bar over 2. So square root, j is always equal to 1. So for Jx, it's going to be J1 minus m there, and then 1 plus m plus 1, so 2 plus m. Alright, and then that's going to be times the direct delta m prime m plus or minus 1. And then plus root, now it's 1 plus m there, and then 2 minus m there. And then del m prime m plus or minus 1. So the Kronecker delta is really acting on both of them. All right. So remember, when you're constructing a matrix like this, you want to run from highest to lowest, from top to bottom and left to right. So I'm just going to write the m values for the matrix. M will equal, okay, so I'm writing m prime, right? So that's going to be 1 1 0 1 minus 1 1 0 1, nope, it's 1 0 there, 1 0 0 0 minus 1 0 1 negative 1 0 negative 1 negative 1 negative 1. All right, and then we'll write Jx based on that, h bar over 2. Let's evaluate m prime m for each one. So the subscripts have to match for the Kronecker delta to be equal to 1. So that means only the terms that have 0 and 1 are going to remain. Right? Yeah. Only the terms that have 0 or 1 are going to remain. So all of these guys in this pattern here are 0. So let's individually evaluate. So we have m is equal to 1 and m prime is equal to 0. Okay. Right. With m is equal to 1, you just have 1 minus 1, so that term is 0. This one is root 2. It's root 2. I think that's going to be a common theme. For this one, m is equal to 1 again, so root 2. For this guy, oh no, actually, for that one, m was equal to 0. What does that mean? That means this term becomes root 2, the first one. And this one, same deal, same deal. It's all root 2. Whack. Alright, let's write the j minus then. Or jy even, which is going to be, in terms of the matrix relationships, I'm going to write an h bar over 2i out here. It was j plus minus j minus over 2i, so this radical remains. With the del m prime m plus 1. And then this radical becomes a minus sign, actually. Plus m to minus m. Del m prime m minus 1. Okay. Looking at our m's and m primes. jy. Again, the diagonal terms are going to go away, leaving that stuff. It's just the op diagonals. So it's m prime m is equal to 1. So that should be minus. And this one should be minus. So then these two are the positive ones. Alright, that's jx and jy. For the eigenvectors and eigenvalues of these matrices, I'm not going to do it in matrix notation. I'm just going to use their definitions and operate them on the basis vectors. So if you choose jx and have it operate on the up state vector, remember that's going to be j plus times the up state vector plus j minus times the up state vector over 2. Jm, it has a very similar thing. Again, it's just the square root of j minus m minus or plus m times j plus or minus m plus 1. For the up state vector, j and m are both equal to 1. So you'll have right here the square root of 1 minus 1, so you have the square root of 0, so that one goes away. You'll have 1 plus 1 for the second term, 1 plus 1 plus 1. So root 3? No, it's 1 minus 1 plus 1. Times 1 plus 1. So it's root 2 over 2 times h bar times h bar. So it's h bar over root 2. And then the lowering operator actually lowers the state to 0. So times cat 0, j m plus or minus 1. My bad. Let's also operate the 0 vector on plus, which means you'll have j plus ket 0 plus j minus ket 0 over 2. For both of these, m is equal to 0. So you'll have root 1 plus and 1 minus 0. So both of them are going to have a root 1 in them. And they're both going to have 2. The j plus is going to raise it to the up state, and then the j minus is going to raise it to the minus state. Root 2 minus over 2 times h bar. So operating jx on the 0 vector gives you a superposition of up and down. Interesting. If you operate jx on the down vector, you have j plus down plus j minus down over 2, which will just leave you with an h bar over 2 root 2 0 vector. So h bar over root 2 0 vector. All right. Then what about j minus? We'll operate the up vector on that, or jy, so it's going to be j plus up minus j minus up over 2I, which will give you h bar, it's minus h bar over root 2I, I root 2, and then times the 0 vector. And then if you operate the 0 vector on it, you have j plus 0 minus j minus 0 over 2I. So you'll have h bar over I root 2 that one's going to go to plus, and the minus one's going to go to minus. Again, you get a superposition, but this one is flipped. And then with j y operating on the minus, you have a j plus operating on a minus and a j minus operating on a minus over 2I. The j plus will raise it to 0, and you'll have h bar over I root 2 times 0 vector. Okay.